Okay, in this video, we'll be going over the pH scale and and kW and the autoionization of water. I'm going to take a little bit of a different take on this and show a molecular view of what happens when you add an acid or a base to water. So first of all, when water is neutral, we have the autoionization of water. So it actually does this. So water will react with another water and it will make H3O and OH. Okay, the amount of these are really, really small. So although this happens, you might think, oh wow, water does that. I didn't know that. But it's so small. So for every two hydronium ions, there's like 10 to the ninth water molecules. So it does do this, but it's super super small. And the concentration of H3O is, when it's neutral, the concentration of H3O is going to be 1 times 10 to the negative seventh molar. The concentration of OH is going to be also 1 times 10 to the negative seventh molar. So when you take the negative log of this number, so the log scale, actually, it's a way to make really tiny numbers a little bit easier to work with, is all it really does. So the pH is, it's just like a convenient way to bring down this exponent. So if you take the negative log, this is how you calculate pH, and we'll be going over this on a separate slide later. It's the negative log of the concentration of hydronium. And as I been saying in the previous videos, you'll usually see it written like this, and that's how I'm going to be writing it also, since H plus is H3O, basically. So, or acidically, actually. So this will be the negative log of 1 times 10 to the negative seventh. And logs are easy when this number is just a 1. So you just bring that number down. So the answer for this is 7.00, which we know from basic chemistry that, the pH of a neutral solution is supposed to be 0. So in my picture, you see that I made 3 hydroniums and 3 OHs. So these numbers are obviously not to scale, actually. So I just chose round whole numbers, instead of like trying to work with this number, just to illustrate this example. So this actually has, you'll notice that the equilibrium arrows, so there's an equilibrium constant associated with this process, and at 25 degrees Celsius, which is normally what acid-base chemistry, around that number is what it happens at. Then we have the Kw, the equilibrium constant for the autoionization of water for this process. So it actually equals this. So Kw, and remember, these are pure liquids. So water is a pure liquid, so it doesn't show up in the equilibrium expression. So it's going to be the concentration of H3O times the concentration of OH over 1. Okay, because the H2Os are pure liquids. So if we know this and this, we can calculate Kw at 25 degrees. So it's going to be 1 times 10 to the negative seventh times 1 times 10 to the negative seventh, or squared. Okay, and it actually equals, so this is what Kw is. It's 1 times 10 to the negative 14th. Okay, so what exactly happens when you add an acid to this? Okay, so it's neutral. Now you decide to add some HCl, okay, or you decide to add some NaOH. I'm just going to use Strong's to illustrate this point, okay, and we can, hypothesize how a weak will behave as well. So it's going to be pretty similar process, just not as extreme. So what happens to this nice happy equilibrium, okay, of these. So just now, this isn't always true of equilibrium where the amounts are equal. It just so happens that when water's neutral, these amounts are actually equal, these two. Okay, so what actually happens is, you're going to, when you add HCl, you're going to swing the balance in favor of these. Okay, and if you add a strong base, you're going to swing this balance in favor of these. So how exactly does it always equal this magic number, this constant? So let's take a look at a molecular view of what happens. So water's nice and happy. We have our nice happy equilibrium here. So we have three of those and three of those. Okay, so just to simplify now, this is not KW, but just to simplify, I have 3 times 3. This gives me 9. Okay, so I need to get basically, we'll pretend for a second that this is KW. This is like our hypothetical KW, just because it's easy to work with these numbers. So what happens when an acid is added? So if you add HCl, then first you're going to get this. So you'll get this process. So first of all, the HCl will dissociate. Okay, this all happens instantaneously. So this will happen. Okay, now if you recall, we had an equilibrium. Okay, so this is our second thing that happened. So this is point number 2, is we had an equilibrium. Well, we just added this. We're gonna mess up this equilibrium. So let's look and see what happens here. Okay, so if I do that, so if I do this, it's gonna start increasing this amount. Okay, so equilibrium gets disrupted. EQ is disrupted. So what ends up happening is all the excess OH. So we need to get, so that what ends up happening is Q is greater than KW, and this can't happen. So it needs to do something in order to lower this amount. Okay, so that when you multiply them, we get 9. So 3 times, I mean, in my example here. So we need to get back to 9. So if we added some H plus, so this is at equilibrium. Okay, and this is when oops, change slide somehow. Okay, so when H plus is added, then we're going to have something like 11 times 3. So we'll have 33, which is way greater than 9. Okay, so I'm going to add some more H3Os here. One. This is my 5th one. 5, 6, 7, 8, 9, 10, 11. Okay, so what happens is this number needs to go down because this is too high. So when you multiply them, we have, like, this is our H plus and this is our OH. So when you multiply them, so this was 3, and now this, since we spiked it up by adding the acid, now we're way too high. So this number needs to go down. Okay, and then this number also will go down. So what happens is the H3O, the newly formed H3O that we have, I'll keep it consistent with the colors. So the newly formed H3O will react with some of these OHs that we have here, okay, and it'll make some water molecules in order to reduce this amount. Remember, we need to get back to this number here because we're way too high. So some of these will be consumed, okay, and it'll really drive down the OH number. The H3O number also goes down too, also. So now what we have is, so those will be gone, and that will be gone. So now if we count it up, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now we have equilibrium is reestablished. Okay, just like Le Chatelier says that's supposed to happen. So now this number, it went from 11 to 9, and the OH went from 3 to 1. Okay, and so now I've gotten back to this is my, Mr. Walls' own hypothetical KW. Okay, just because I don't want to work with those itty bitty numbers. Okay, so just to illustrate this example, okay, then we got back to our original equilibrium number. Okay, so what ends up happening, as you can see, is we have a whole bunch of H3O now. Some of it did get consumed, and it ate up some of the OHs that were there from the autoionization of water. So it did that to drive this down Meanwhile, this is still much higher than this would be. So what we end up having at this new equilibrium is we end up shifting the amounts, but KW is the same. So the amounts are no longer equal, but KW is going to be the same. The product of them is going to be the same. This is true when we have a base also. So the same thing will happen. It'll drive the H3Os down, and then these go up when we add a base. But when you multiply them, it's got to get back to equal to KW. Okay, so when you have an acid added, then we have H plus ends up being, or H3O ends up being greater than the concentration of OH. But the multiplication of them will always equal KW if it's at 25 degrees. Okay, so and then our pH will end up being, so if you take the negative log of bigger and bigger numbers, you get smaller results. So this is going to be less than 7, something less than 7 if you have an acid. Okay, so let's do a similar analysis when a base is added. Okay, so if you have a base, we'll make this the new base purple, I guess. So if you have like NaOH, so we add some NaOH. So this is going to dissociate. And this is a spectator, so we're just going to omit it from this picture just to simplify things. So the OH is what gets added, okay, and a similar thing takes place as to what happened before. So these spike up, 1, 2, 3, that's 6 total, 7, 8, 9, 10, 11, okay, and then we had our nice happy equilibrium again. So we had H2O. So this is our nice happy equilibrium, and we just messed it up by adding this OH. So this is going to go like this and this, okay, and then we get H3O OH. Now we just jacked this number way up, okay. So so now we have Q is greater than KW again, which can't be, Le Chatelier says. So these are going to, this and this are going to react, and then let's react another one, okay, until it gets back to our magic number. So it was at equilibrium. We had 3 and 3 H's or H3Os and 3 of those. So my hypothetical KW for my example is 9. Now we just messed it up. So when OH is added, then we spike this number up to 11, and it's no longer 9, it's 33. Okay, so if we consume some of that H3O, so the OH will eat up some of that H3O, and it'll form some waters. So it's going to decrease that and knock it, or this will go down a little to 9. And then the H3O, so here's equilibrium is re-established. So it's that 9 will knock down because 2 of them consume, so that go down the 11, so it goes down to 9, and then these gets knocked down to 1. Okay, so we re-establish my hypothetical KW here. So your OH now, this time, as you can see, your OH is much greater than your H plus or H3O. Okay, and if we take the pH of these smaller and smaller numbers, we're going to get larger results. So the pH is going to be something greater than 7 if we do that in this case. Okay, so there's a list of equations that we can use as a result of KW. So let's go on to the next slide. So these are some of the equations that you'll be using, and we'll be really familiar with these when we start doing acid-base, like weak acid ice table equilibrium problems. So you don't need to memorize them, but you'll be so used to them that you'll just kind of start knowing them. The relationships between H plus OH, KW, and pH. So first of all, we have this Kw is the product of OH concentration times H plus concentration, or H3O. And this is 1 times 10 to the negative 14th. This is defined. So this is a definition. So what that means for sig figs is you have infinite sig figs because it's an exact number. In infinite sig figs, because it's exact. Okay, then we have, of course, the pH equation. So that's negative log of H plus concentration. And we also have pOH. If you take the negative log of the hydroxide concentration, that gives you something called pOH. Then if you take the inverse log, if you have the pH and you want the concentration, you would take the inverse log. So which would be 10 to the power of the negative pH, and that would give you that. And then we have the corresponding OH as well. Okay. Lastly, if you use log properties for this equation, so these two are directly related if we use some log properties. This one and this one. So if we use some log properties, then we'll have this. We'll have the pH plus the pOH equals 14 point. And I'm going to put 0 and a dot, 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 because this is exact. So it has how many ever decimal places as you want. The other number, like you'll see when we start doing problems, will be the one that limits your decimal places when you add and subtract using that equation. Okay, one more thing on how sig figs work when you're doing logs. So this is sig figs for logs. If you have the hydronium concentration, and let's say, for example, the pH of something was like pH was 6 point. Let's say the pH was 6.77, and you want the hydronium concentration. You want to convert that to hydronium concentration. It would be 10 to the negative 6.77. So here's how this works. It's the number of decimal places are going to be how many sig figs are in your answer. So if you type this in your calculator, you'll get it. You should round after the second sig fig, 1 times 10 to the negative 7th molar. So our result should have 2 sig figs since the pH had 2 decimal places. Now, if you go the other way, it's what you might think it is. It's the opposite of that. So if you take the negative log of, say, that's your hydronium concentration, then it's going to go number of sig figs. So if this has 3 sig figs, then your answer should have that many decimal places. So if that has 3 sig figs, your answer that you report should have 3 decimal places. Okay, so now I'm going to do a example problem. And the year turn is very similar to this. So it says the pH of a sample of human blood was measured to be 7.41 at 25C. Calculate the pOH, the H plus, and the OH minus concentrations for this sample. So there's probably a number of ways, because we have 4 different equations that are all related. So there's a number of ways you could do this. So I'm doing just, one of those several ways that this can be done. So they gave us that's our pH. Now, if you remember that it's an interplay, if you look back at the beakers that we drew in the first 3 slides, it's an interplay. So if you have like this teeter-totter and your H3O goes up, so if it's at equilibrium, Now I can only do this because these are equal at equilibrium. That's not, of course, true at all equilibriums. But if this teeter-totter side, if this increases, okay, then this is going to decrease, and then vice versa. So when you multiply them, they always equal kW. So it's related on that finite scale of 14 because of the kW of water. So because of that, I can do this. So if I want the POH, so they asked us to calculate POH, that would be 14 minus 7.41. Okay, and for that I get 6.59, 2 decimal places. So next thing I want is H plus. So this is going to be 10 to the negative pH. So it would be 10 to the negative 7.41. And since I have 2 decimal places, my answer should have 2 sig figs. So I get 3.9 times 10 to the negative 8 molar. Okay, so this is 2 sig figs because I had 2 decimal places. Okay, so that's that answer. Lastly, I need the OH concentration. So there's a couple ways we can do it since we have this and this. You could go 10 to the negative POH and plug in this number. Or you could do it this way. You could go OH using, I think it was equation number 1 on slide ago. You could go KW over the H plus since we solved H plus just now. Okay, so it doesn't really matter. And let's see, you get, where was my H plus? 3.9 times 10 to the negative 8th. Okay, and for this I get 2.6 times 10 to the negative 7th molar. Okay, so the year turn is pretty similar to this. Okay, so here's the year turn. Okay, that's the end of our video.